Good morning. It's enzyme time. I know you're excited. Here we go. They are what make you tick, so you should be excited. So, first of all, we identified that enzymes are proteins. They're not carbs, lipids, they're proteins, right? They are catalysts. Catalysts make things happen. That's their general definition. But in this case, these chemical catalysts make chemical reactions happen faster than they normally would. They don't make impossible reactions happen, and they don't really make them happen. We're coming to that in a minute. They make them happen faster. There's other things that make chemical reactions happen faster. Heat, you do that in chemistry labs all the time. You heat it up so it happens faster. But we'll come back to heat and why these enzymes are such key catalysts in the reactions of living things. So often their names, not always, end in the ending ASE, which is kind of close to OSE, like carbohydrates often end their names with OSE. So we'll be on the lookout for that. Here's some vocab. This is extra, no charge. This is not, in other words, EOC stuff when I say that extra, but this is honors biology stuff. So the word catabolic and anabolic I'm going to use and keep coming back to. Anabolic steroids, you may have heard of. Those are those kind of lipid sterols that are really like fake testosterone, and they help build up your muscles. Anabolic means build up. Here, what that means is that chemical A and chemical B are getting put together in a chemical reaction, represented by that arrow, to make something different. And this would be something bigger, right? Anabolic means put together two smaller things to make a bigger thing. Catabolic's the other way around. Take something and break it into smaller parts, all right? So now we have energy is going to come into play a lot here in this unit. Exer means out of, just like exo, but this is exer, same kind of thing. Gonic is an energy word. That means if this reaction, A plus B, combines to make C, right? If that requires energy, we have to add energy to make this happen. That means energy didn't come out of this reaction. We had to put energy into it. What would that mean? Or excuse me, what would the word be for that? Endergonic. So what does exergonic means? That means if you take molecule C and you split it up into A and B, and that releases energy, that would be exergonic. So catabolic reactions are usually exergonic, anabolic ones usually endergonic. Now we're going to talk about chemistry in general real fast. Here's two chemicals, A and B, right? If they're going to combine with each other, they have to bump into each other. They have to collide. It took a long while for us humans to come to this explanation, which is what a theory is, based on lots of information and data, right? Because these things are invisible. It took us a long time to figure out that they existed, much less how they work. So we came to this simple idea called collision theory. If A and B have to collide to form C, then anything that will cause more collisions or more forceful collisions will make this reaction happen faster. And faster reactions are kind of all about what this is about and what we said catalysts are. They make reactions happen faster, but it's collisions that make reactions happen. On the other hand, if C is going to split into A plus B, right, a catabolic reaction, right, exergonic, right, then something has to bump into C. It's not just going to split all by itself. So collisions are what make reactions happen. Now we have this idea. Sometimes to make a reaction happen, even if it gives off energy like this one would, we have to give it some energy to start it off, to activate it. So if I was in class right now, I'd hold up a Cheeto and I would light it with a match. And you would see that Cheeto burn and a whole lot of energy comes out of it. Where was that energy? It was in the bonds of that Cheeto. How did we get it out? By breaking those bonds. and make little other pieces of Cheeto that are up in smoke, so to speak. But to get that started, we had to add a little energy to get it going. We'll come back to that in just a minute when we look at a couple graphs, because in the next slide they're going to have an EOC threat to ask you about graphs. So here we have some chemistry words. You've had these before, I think. The chemicals you start with are called reactants. And in this case, the chemicals we start with, they have made of these little models. They are AB connected together and CD connected together. The chemical reaction symbolized by this arrow is going to change them into these products. You can see this is an exchange reaction. This is, you're going to call this next year in chemistry, where these they're just like switch partners. Okay, so some bonds have broken. These bonds have broken, but some bonds have formed. So this is kind of like a little bit of endergonic, a little bit of exergonic. But here's the energy idea. This y-axis is free energy. What's that mean? Well, for us right now, we can think of it as the energy that's in these bonds. And what this graph shows is these reactants have this much free energy. There's no numbers on here, but it's that much. And the products had less. In the course of this reaction, the chemicals lost energy. That means that energy was released. That means this is a graph of an exergonic reaction. Okay? But if this is like the Cheeto, and it very much is, if this is like the Cheeto, in order to get it to burn and release that energy and break up into those products like ashes and carbon dioxide and other gases, right? We had to light it with a match. We had to energize it. We had to add this activation energy to it, and that's what the match provided. Well, we can do that in the lab, but if we're talking about the chemistry that happens inside of you and I, that wouldn't be a good way to catalyze those reactions to make them happen faster, right? Your lunch, for instance. Your lunch is going to get digested. That's a chemical reaction. That's a break apart catabolic reaction. One way we could get your lunch to break apart is to light you on fire, just like the Cheeto. That would do it. But that wouldn't be good, because that fire would make all kinds of reactions happen. And life is not random chemistry. Life is very specific chemistry. For that thing we humans have defined as life to happen, you have to have this reaction happening now, that reaction happening later. And so fire and heat as a catalyst to make life reactions happen fast enough is not good, because it's not specific. Okay? So another way to look at what would happen brings in a word that we had before. If we lit you on fire, lots of chemistry would happen, including lots of big chemicals getting broken up, getting changed from their natural shape, denatured. Like an egg. When you cook an egg, all that clear stuff that we call egg white, well, it's not white until it cooks. And what the heat does is changes the shape, breaks some bonds and things, of the shape of a protein named albumin. Egg white is almost 100% albumin. There's also quite a bit of albumin in your blood. It's part of what makes your blood sticky, for instance. But the egg now has had that protein denatured, and when you cool it off, it's not going to go back. Now, albumin is not an enzyme, but like albumin, if enzyme proteins were broken, usually denatured, usually they're not going to go back to their shape that they were, their shape that was their working shape. And why shape is important is coming up in just a minute. But right now, back to energy. So this is a graph that, unlike the one we saw before, although it's obviously very similar, is more likely to show up on a test. And here's where, remember I said anytime you see type in red, that's straight out of the EOC syllabus. Here's where they threaten to ask you questions to be sure that you can recognize various graphs. We'll talk about those various graphs in a minute. But first we're going to talk about this graph, and that's the one that has to do with activation energy. All right. So explain the role of enzymes as catalysts that lower the activation energy. Okay. So now if we went back to the other graph, we don't really have to, because if you look, it's on this graph. The black line is the same as the graph we just left. Okay. That shows the energy dynamics. If we take reactants, add energy to them, light them on fire, and then when they start reacting, the reaction results in products with less energy. But we said that's not good for living things, because if we had to add this much energy to make this reaction happen, then we're going to make a bunch happen we don't want to. So in red here, you see what an enzyme does. There is an enzyme that's just right for this particular reaction to happen. And what that enzyme does is not add energy, but it just reduces the amount that's needed to have this thing go, which is kind of like falling off a slide, right? That's going to happen all by itself, just like the Cheeto burning. But like the slide, in order for you to slide down, you first have to use energy to get up. That's kind of like adding the match energy and getting it to a state where it can then slide down. It's a good analogy, all right? So this is what enzymes do in terms of energy. When you're asked, explain, that means gives reasons why something works, in this case enzymes, making reactions happen faster. Your explanation can be in two different directions. The energy one we just talked about. But how it does that, how does it make this reaction happen with less energy, that has to do with mechanics, meaning what exactly is this molecule doing? And that's what we're coming to in just a little bit. So, like I said, in terms of energy, enzymes do not add energy. Common misconception, right? They lower the activation energy necessary, and therefore a reaction can happen easier and therefore faster than it could have without the help of the enzyme. So now at your relatively moderate body temperature, you can have reactions happening if they have an enzyme helper, and that's what allows specific ones to happen at a specific time. That is a very simple definition of life. Because if that ordered chemistry doesn't happen well ordered enough, that's really a chemical definition of death.